tries. Okay. So it tries to utilizing the neural network as a module and represent the knowledge as continuous embedding and conduct the reasoning in discrete space, very similar to our like what we previously conduct in the SGN. And another direction is somehow a more new direction, which tries to just utilizing the self-supervised pre-training to train like a super large like language model or something else, and which it can incorporate in all of kinds of the knowledge, and it tries to like changes the task formula to be similar with the pre-training, and in NLP it calls a prompting, and tries to distill the learned knowledge from the pre-trained knowledge model language model to deal with different tasks. So that's beginning. So firstly, I'm talking about LEGO, the latent execution guided reasoning for multi-hop question answering on knowledge graphs. So actually, it is like very similar to what I have been been trying to do for like the past years, and it is conducted in the by Ren Hongyu in his summer project in Google. So the basic idea is trying to utilizing the logical reasonings approaches to deal with natural language question answering on knowledge graphs. So particularly given the question like where did all Canadian state citizens with Turing Award graduate? So people can parse this query into a more structured logical forms, like in like the first order logic query in shown here, and based on this, we can execute these like logical queries on the knowledge graph by discrete graph traversing or in the continuous space via the recently proposed many like methodologies about like the graph query embeddings. We have discussed this before by Shirley and many peoples. But the problem here is that to train such a system, we need some like the supervision of the intermediate logical queries for the natural questions data sets in the literature, like different like open domain QAs. Mostly for these questions, we don't have such intermediate logical queries. So earlier people tried to utilizing the RL approaches to discretely search some queries to deal with each questions. However, such approaches will be problematic. First, it's because the reward might be under the specified. Some wrong queries may also get the correct answers by mistake, but it might not be the ground truth ones for each questions. Also, since most of these approaches are conducted in discrete space, so it's hard to generalize to new questions and cannot utilize in the continuous space reasoning module. So this work tries to combine like the knowledge graph query reasonings works that Hongyu has done into this question answering problems. So the basic idea is that the query synthesizer and the latent executor shares the same neural modules, and it can utilize in the trained neural modules to generate the queries and also conduct the reasoning to get the answers. And so there are many two research questions that I have summarized. So first is how to get the answer on KG given the query. So basically it is just a copy of query to box. And in this work, they only utilizing the intersection operation. The second question I think is more important is how to train the model by synthesizing the queries from the questions in natural language. So as I previously stated, it's a hard problem as if we get wrong queries, but you can still get the correct answers. It might mislead the model to capture some like incorrect rules. So we need to find out a way to like synthesize more accurate queries. So for the first part, how to get the answer, I assume that most of us are familiar with the query like query to box methodologies. And in this paper, they changes a little bit to be more like suitable for generating the queries. It's because that in the query to box work, they will assume that the query template is fixed. For example, most of the queries are given two entities, and each entity have a relation forward, and finally they do the intersection. But in real cases, we don't know the intermediate queries, so we need to predict at each stage which action we need to do. And in this paper, they mainly consider two different actions. First, at each state, it defines the currently branches from B1 to Bn, which is like n entities at each stage, and given this like n branches, they will have two different operators. The first is that for one branch, you can take the relation projection. For example, how to move forward? Oh, sorry. For example, given like the this Turing award, if we want a relation win, then we can get all the persons that won the Turing award. The other action is conjunction and or intersection. So basically, it's that they took a subset of all the branches in the current state and will like conjunction these different branches together to be a single unit. So the key problem here is that how to select a subset to do the conjunction, because that we have like the different like the different enumeration of different branches, so that they firstly parameterize which action to do as the p theta given the current state question and the branch state, and they will predict which branches they will select and which relation they will do it forward. If the R is minus one, it means that they will do like the intersection. And the most important question here is which subset to select. So it requires to get a set embeddings. So they simply utilizing a deep set of operators, which is somehow similar to the mean pooling or max pooling over multiple entities. And after that, they will get a setting like the set embeddings for each combination of the power set of the branches. And for each of them, they will predict whether they're utilizing a certain intersection operations. And after that, they would just select the one that predicts have the highest probability to be intersected. And if the all of the intersected probability is somehow smaller than some threshold, then we're just utilizing the relation projection. And after I introduce how to like construct a query from a natural questions, the next key problem is initially we don't have a very well-trained model to synthesize such good queries. So how can we initially get some good queries to help to train these models? So this requires some extensive searching from, for example, given the initial set of the entities, like we mine from the questions. A naive way is that we can do like breadth search or some other heuristic search to get multiple discrete queries. And for each of them, we can measure whether it can correctly answer these questions. However, there are too many problems. First is that such kind of the searching has a very large searching space, especially for a knowledge graph, which contains about thousands or more of the relations. The searching space is super large, consisting considering like we also have intersection operators in between. Another key challenge is that, as I said, some wrong queries can also lead to the correct answers. So we need to like filter out those incorrect queries. So in this paper, they propose for the first question, they propose some pruning methods that that can be pre-trained on the knowledge graph is only, and utilizing this pruner to narrow down the searching space. And also, after they get the queries, they will re-rank those queries based on the current trained models. So let us first discuss the queries, the pruners. So the pruners are in two levels. One is the branches, the other is the relation. For the branch, it is like they will judge whether at each state if the searching agent give us the action that it wants to like union multiple entities, this pruner will predict whether these entities are similar enough to be like union together into a new set. And based on this, it can like prune out those operators that are not like correct enough. And the relation pruner is like for each entities, it will only give, allows the searching agent to give the relation node that are more similar to, that are more like coherent with this entity node. For example, if we have like a person, then most likely we don't want some like the other relations that are should be annotated to some non-person entities like fed or like located. So first, let's discuss about the branch pruners. So this pruners tries to predict whether two entities should be put together. So in this paper, they claim that if two sets or two entities are very distant from each other, which means that they are not very similar to each other, then they should not be like put together to be union together. For example, if we have a Nobel Prize node and one like US and Canada nodes, these two nodes are not very similar to each other to be described as a similar entity or prototype. So in the query toolbox modules, these two sets should not be union together to form a new box, because in that way the box will be super large. And they will try to pre-train a so-called branch pruner that take two sets together and predict whether these two sets should be could be unioned.
Daniel, may I ask a question here?
Yes, sir.
Yeah, so I think it's not quite clear to me what would be the assumptions to the valid query tree structure. So in other words, right, so in the second question, like we wanted to convert the text into a query tree, and that involves some sort of search. So that's why we want to do some pruning. But I think in the beginning, we need to understand, or like try to use some example, right? Try to understand what would be the valid space. And for example, in the box embedding, actually, I think in the early stage, you mentioned that we only consider intersection of two boxes because the intersection of two boxes are still a box. But if we consider union, right, then it's not going to be a box. So if we have this sort of assumption, then we can only handle one very special type of query, right?
Yeah.
It just so what are the assumptions here? What would be the valid space for the query tree? So then we probably can understand better the like solution part.
Yeah, in this paper, actually, they didn't discuss this very clearly. So from my understanding, like firstly, they only consider the intersection operators. And second thing is that when they do the intersection between two sets, they want to avoid these two, after intersection, the output is empty set. So like, for example, if one set is like a Nobel Prize by Obama win, and the other set is more like discussing about some location or countries by Obama born, then these two sets, since they are very different with each other, after doing the intersection, most likely the output will be an empty set. So this is what they want to avoid when they do like the searching.
Yeah,
so
this is also kind of not that natural because it's possible that for some query don't have any answer. In other words, the answer set is empty set. It's quite possible, right? So then I just wonder, how could we push this kind of constraint? This constraint say that we wish that we see something in the answer set. How we can push that into the pruning stage? I feel we should follow the natural language query and try to decide which two sets we want to do the intersection, right? So like natural language should guide us instead of this, we want to say some non-empty result, this kind of constraint guide us to get that query tree. I just feel this is very unnatural to me.
Yeah, that's a very great intuition. Like, from my understanding, when they synthesize the intermediate query, so They only deal with the natural questions where for each question they have the like the unique answers. So it means that there is no such answer for this question answering data set. There is no such yes or no questions. All of the questions are like a specific entities. So this is more like an entity-centric QA data sets. This is why I think they give this intuition that when they like construct the queries, they wishes that all of the intermediate state have at least have some entities. Yeah, this is one thing. Also, I think that maybe another more like a high level way to design such constraint is like, for example, the type or property of two sets should be similar. For example, this is like a correct queries, like a, all of this V here should be the person. For example, all of the person that is citizen of the Canada, or all of the people that are won the Turing Award, all of the people that graduate from something, all of these output entities like share the same like a hyper property or ontology, like they all of them are person. I think this is a more natural like a way they should have a constraint on this SAS output.
Right.
Yeah.
That makes more sense.
Yeah. But in their design, they didn't explicitly model this kind of the high level type of the sets. I think this is why they just utilizing the comparison between two set embeddings to decide whether they are like coherent with each other to do the integration. Yeah.
Okay.
Okay. So I think I have like explained how they do the pruning for the intersection. Another thing is about how to like decide whether we should add some specific relation to a specific node. I think this is more natural because for some of the type of entities, it can only be linked with some type of the relations. For example, in here they show that given the current state as US and Canada, this set should be represented as all of the countries. And this countries node should only be like linked with some relations such as capital or anthem, and it shouldn't be linked with like the relation that associated with a person like the recipient or is president of something like that. So this is why they can utilizing this pruner to as a neural network to given the a set as input to predict what should be the set out relation set output that should be attached to it. And I think the most important thing about this part is that both these two pruner can be pre-trained solely based on the knowledge graph itself, and we don't need some annotated languages or like those queries, because as I said, all of this set and like the entities are like the high level of concept in the knowledge graph instead of like the words. So given the knowledge graph with some relation link, we can synthesize some of these kind of training samples, and we know that given two sets, whether their output is empty set or not. So in this way, we can construct some positive and negative examples to like pre-train such pruners. And for relation, it is also the same. For each of the node in a set, we can know what are the kinds of the relations that attach to it, and we can based on this to like train like the discriminator to predict for each entity what kind of the relation it should be attached. Okay, so given this two pruner, this paper can shows that it can run like the random searching like the Bing search very efficiently. And after that, for each questions, after they get multiple intermediate queries, for each of them, they can get a final output embedding output like the query embeddings for each kind of the query. And they can like conduct similarity search of this query embedding with the final answer to justify how well this query can be used to answer this question. And they can sort it by this probability and only select the top k. But another problem is that this kind of the, as I said, some of the queries also like can answer these questions, but it can mislead because it is the intermediate logic is not correct. So they also utilizing hard EM algorithm to utilizing the currently trained model to predict what is the likelihood of the model to generate these queries. If the model have a very low probability to like reproduce or generate this query, then probably say that it is not coherent enough, and they only select the top end of the queries that could be highly probability to be generated by the current model as a training data. Okay, so this is like their high level training algorithm. They will firstly pre-train the latent space executor, including the entity and relation embedding, by just running the query to box or the other like the query embedding algorithms. And then they can pre-train the branch and the relation pruner based on some synthesized training samples from this knowledge graph. And finally, based on the given the training data set that each Q is a natural question and each A is an entity in this knowledge graph, they can search the candidate queries for each training questions utilizing this they call it execution guided pruning, and they can record the top K ranking query trees and their traces in the buffer, and utilizing this to train the model executor. And this is like
I have another question. So I still didn't see how the signals in the natural language has been utilized. So if we know the entity and the relation, right? So of course we can just apply the solution to the first question to execute that query tree, and then we can get an answer. We can compare to the label, right? But how the structure has to relate it to the question text as well. So what I can see here is like once we get the query tree, then we can compute everything and then compare to the ground truth. But how we can leverage the queue itself?
Yeah, so by looking at here, so their model is something like the inductive model that can take input queue as input to something like expand these intermediate queries. So what they do, I think they didn't explicitly state it in the papers, maybe in their coding implementation, they will discuss it. But from my understanding, maybe they should utilizing some BERT encoder or something else to encode to get embedding for these questions and concatenate with their intermediate state to predict what is the next action they should conduct. So,
for example, we have to at least know what should be the entities, right, and the potential relations that I can read out from Q.
Yeah,
it's like by doing some pre-processing, how we can align the entities mentioned in Q and the entities mentioned in the knowledge graph.
Yeah, it is also not stated in the paper, but I assume that they should utilizing some initial entity linking to get the initial entity from the question. This is not a very hard task because most of these KBQA dataset, those questions have a specific entity in the knowledge base. For example, in the Wikipedia, we have some person. So so that they can, I think they should have an initial entity set on over the questions. And from that, at each state, it will utilizing these entities as the d theta b, and also the questions embedding as q together to predict what is the next action to do. And they will train this model based on the queries they searched. After the model is trained, given a new question, I think they can step by step construct the correct query graph.
Mm-hmm. Yeah, so to me, it's like from Q, we can generate some latent graph structure or tree structure, which is a query or computational graph for the query, right? Mm-hmm. And then we can, based on some operator, for example, query to box or what Shirley has developed to compute answer for that computational graph, right?
Yeah, so I think the difference is that this paper, also similar to my previous project, is do this by step. So they didn't solely based on the queue to construct a whole query tree. Instead, they are doing things like expansion way. So at each state, they will based on the question and the current state to expand the next action. And step by step to because as you see, after they expanded the B, they will like update the speed state by adding, for example, new entities, or like after they do the intersection, or some of the B will be union to be a single entity. And after that, the next state will be also dependent on the state update, but not solely based on the question.
Okay, got you.
Yeah. I think the way you describe is more like the traditional parsings that would just based on the question to synthesize the discrete parts, the tree. But the question there is that they don't have too much of the label data. I think this is why in this paper they propose to unify the question execution, like the query to box, with the query generation.
Yeah, but I feel what I describe is also similar to or related to structured learning. We don't have to have the label for that, as long as we have the label in the end, right? So as long as we know the answer to the query, then we should have a way to find the best graph structure for that query.
Yeah. I think the major challenge here is that the searching space is much larger than the traditional, like the graph, because in here we have also have the label for each edge, for example, like different relation. So doing this kind of a searching is much harder and hard to optimize.
Yeah, let's see. Okay, probably there should be a way. Mm-hmm.
Yeah, so this paper only conducts some like the analysis on KBQA data sets, such as a MetaQA and WQSP and the CWQ, the web question and the complex web questions. And over this, and they explicitly remove some of the edges from this this KB, because that if all of this KB is complete, then actually some of the existing KBQA data set can achieve a very good performance. I think this paper emphasized more on if the KB is incomplete, then their query embeddings approach can somehow get better embeddings to like infer some missing edges. And over this incomplete KBs, their performance is better than the existing data set baselines, such as the heuristic traversal baselines and some of the embedding-based baselines. And they also add some ablations that whether the pruning and the hard EM is useful. As you can see, the pruning is super useful here, because without the pruning, the searched out queries are most likely to be like incoherent by itself, so that they cannot get very good results. And these two tables shows that for all of these queries from like the pre-training stage, after they pre-train these pruners, how well it can predict for each of the queries it is correct or not. As you can see, their pre-trained pruners can give out a very good accuracy to predict whether a query is by itself is correct. Okay, so this is about this paper. Actually, I think this is by far the first and the only paper that tries to combine the query answering, query embeddings approaches with the natural question QA. So probably we can, if we also want to like conducting like the research by combining the graph with the natural QA, we can somehow draw some inspiration from this paper. Okay, so next I'm going to discuss a more different line of research, which tries to inject some learned knowledge from pre-trained language models. Actually, recently there's a large branch of works trying to do in this line, and I just pick up a recent work from this line of research and introduce the basic ideas. So all of the line of research are called the prompting, and actually Professor Jie Tang have done a lot of work in this line, and the basic idea is that we have a very powerful language model, for example, GPT-3 pre-trained on large scale, like the language generation task or like the mask language model task. And based on this super powerful language model, if we want to deal with some different downstream tasks, there are two formula. One formula is more natural, like we take out like a summary embedding, for example, the first embedding of a sentence, and utilize this as a summary of the whole text to do the task. And we will do some fine tuning on that. Another more interesting formula is we can utilizing a prompting. For example, if we want to do a machine translation, we can add a task description like, please translate the following sentence. And if the language can learns how like the meaning of this description, or they call the prompting, then most likely we don't need a very like extensive fine tuning to be able to adapt the pre-trained model to different tasks. So here I describe some of the more easier to understand prompting, which is like if we want to translate English to French, then we can add like the dot line here from the source entity to the next to the target entity, and by just adding this source entity and the dot line, GPT-3 is able to like infer the target entity as the answer. So a lot of like work have tried to explore whether the language model can be used to do this kind of knowledge compilation. And recently there's more work that tries to utilizing this formula for all the different tasks, which is what this paper tries to explore. And GPT-3, when it's published, it is a very gigantic language model. And when it does like the zero-shot learning, it will just freeze the model parameters and utilizing some manually designed prompts or some templates to do different tasks. And also there's recent some other works that tries to utilizing a smaller language model such as BERT or Roberta, and given the prompt, they can utilizing the prompt to fine-tune the model. For example, if we want to do a sentiment classification, then we can fine-tune the model to force it to predict a positive sentence to be positive and negative sentence to be negative. And this paper tries to explore whether we can automatically learn the prompt or the templates that can teach a pre-trained language model to deal with different tasks. Okay, so firstly, maybe I can give out some example of the prompting previously people use. For example, for many of the sentence classification, after a sentence, it can just add it was and add a mask here to ask the model to predict whether it is a positive or negative sentence. And they will have some label words such as for positive it is great and negative it is terrible. So that if given the sentence it predict it was great, then it means that it is a positive sentence. And also it can be deal with some more complex task like to predict whether a task entailment is, for example, whether for a task for a sentence and an entity, whether it is entailment relationship, and whether two sentences is equivalent, or whether like two sentences contradict with each other, or even some more complex data sets such as question answerings. And the advantage of this kind of approach compared with the traditional fine-tuning is that for traditional fine-tuning, we need a specific task-specific layer. And in this way, it requires some added parameters. For those of the zero-shot or few-shot task, those very small labeled data sets are not large enough to train even these task-specific layers. However, for this kind of a task, since they're like the inference paradigm is exactly the same with the language model prediction, so we don't need any like the task fine-tuning with added parameters, so that we don't add any parameters, just you pick up some of the anchor words and just to judge whether this prompting can teaches the models to predict whether a sentence is positive or negative. Okay, so firstly, let's look at how well the traditional prompting methods do given like the human-defined template. Actually, by enumerating the label words, they can achieve relatively good results, even compared with some of the fine-tuning methods. because for some of the data sets, the label data is not large enough to fine tune a very good task specific layer. So this is a very impressive result that when it first comes out, that utilizing a fixed template and some label words, they can achieve better results than doing a fine tuning. However, picking up the different like the template or the correct or the best the prompting words, like the influence the final accuracy a lot. If the model chooses if like the human choices are not good enough, like a template, for example, hypothesis with a question mark and mask, then premises, then this kind of the masking, this kind of template, although it looks reasonable from human side, but it didn't perform better than some of the like the other searched templates. So this raises the question whether given like the already trained the language model, we can automatically find out the best template and anchor words to conduct this kind of prompting fine tuning. Okay. So there are two tasks here. One is how to select the best label words. The other is the template they will try to utilize use for prompting. And for label word actually is a relatively simple task that for each of the sentence, for each of the training samples and a given template, we can just utilizing the gradient methods to judge whether if we choose this one word as an output, whether it fits the correct answer, like a true, like a positive or negative. For example, firstly, for each label, it can take top keywords with highest mask language model probability conditioned on training examples with a label, and then enumerate all combinations pruned by the zero-shot results on the training sets. For example, given like all the positive words and the negative words, they will try out different enumerations, and based on and if they didn't just based on the zero-shot prediction results, which is that they didn't fine-tune the model based on these words and see whether these two pairs of the words is coherent, is correlate with the true or false labels, they can prune out a set of good candidates. And after that, they can fine-tune the generating model based on these candidate sets. The fine-tuning can be done by given these good samples and the bad, good word and a bad word. For example, a word as good or a word as bad, they tries to fit the probability to be good for those positive sentences and forces those negative sentences to be bad. And after that, they can fine tune this this generative model based on each set of label words, and then evaluate the performance of each pair of the words on the development set, and finally pick up the best pair of the words. Okay, the next question is about template generation. So the template is in their cases is more like the natural language, with some of the special token here. For example, X and Y denotes like not here. For example, in here, the X should be like the starting token of the sentence, and Y could be the ending token of the sentence, and Z, and in between, we can have like the a judging, like a prompting words, and a Z could be like the words like maps to the label words that we previously mined. So the way that they generate this template is by utilizing the fixed T5 model, which can tries to generate the fill-in blank words from given the sentence. So that, for example, given a thank you for something, me to your party and mask, it can the T5 can already generate in the missed out words like for inviting and last, and they're utilizing the pre-trained T5 to generate the fill out template for each prompting. For example, suppose we have a data set for like sentiment classification. So firstly, we can add a sentence and add the label words we previously in mind as, for example, great or terrible here, and put an X and Y before and after the prompting words. Then it feeds out into the T5 and tries to decode the missing X and Y. And this is the template they generate for the sentiment classification task. So it should be like, for example, a fine ride, a great one. So the final words to be generated is very simple. It's just a simple A and a simple one. So, but it can already be a natural sentence to describe whether each description is a good or a terrible one. Okay, and utilizing the T5, they can fit the T5 to be conditioned on all of the training examples to find out the most probable of missing blank words here, and utilize this as the final template. Okay, and after they generate the label words and the template, another question is how to do the fine tuning. So in the original GPT-3's paper, they show that instead of just fine tune on each single sentence, a better way is that put the sentence in the context. They call it in context learning. For example, suppose we're still doing the sentiment classification. Instead of just doing the fine tuning solely based on this single sentence, they can put this sentence together with some other sentiment classification sentences. And by, for example, for no reason to watch it is a negative sentence, and by putting it together with some of the other similar sentences, with some of them are more positive and some of them are negative, then it can know it can tries to learn what is the keywords that forces this sentence to be positive or negative. Like the GPT-3 paper called it in context learning. But originally, in GPT-3's paper, they only randomly sample the examples in the dataset and fill them in the context. And recent some works also show that by putting the sentence more similar, syntactically similarly to to each of the target sentence we want to learn, it can give us a better prediction results. So in this paper, they simply utilizing another SentenceBERT module to somehow quantify the similarity between two sentences, and only pulled out those sentences are more similar to a target one, and put it together and put all of this together as each batch to do the fine tuning. Okay. So till now, I have introduced how they can generate the template, generate the label words by searching, and how by given this template and the label words, how they can do the fine tuning. Is there any questions so far?
So I try to understand the major contribution. Is the major contribution try to turn this regular task into this language task, so then they don't have to introduce additional parameters?
Yeah, for this prompting idea, I think the major contribution is actually, as you said, so they in this way, this kind of the downstream task is more similar to the pre-training task, so that if we have a new task, most likely we don't need any further fine-tuning or further like the we don't need further fine-tuning, so that even for a task we don't have any label data, we can still have a relatively good results. And to do that, a major question or challenge is to select a good prompting words or a description of this task. And traditionally, people just human define some template, and this paper tries to automatically learn the template.
Yeah, I think I missed that part, because I think the goal is still try to, for example, have I think in the original task, right? So they still have the sentiment analysis task, but then they don't want to fine tune those tasks because it introduces additional parameters as shown in the slide. Then they wanted to automatically generate some templates such that it can turn those, for example, positive label and negative label into words like great and terrible.
Yeah.
But I didn't quite get like why. Yeah, I can understand like manually how we can do that, right? I just do not understand first why automatically generate those templates would be better. And second, I think I still missed the part how they when they say, okay, I'm going to automatically generate, what kind of criteria that they are using.
Oh, so for the first question, why automatically generate is important is because we previously have some empirical analysis that for different tasks, choosing different template, although we just switch some not very relevant words, can influence the result dramatically. So it means that I think the pre-trained model is somehow sensitive to the template we select. So we cannot just by our human to select some prompting words or the templates, and based on their automatically generated template, we can achieve the most optimal results for each task. And the metric they utilizing for selecting both the words and the template. For template, I'm not quite sure, but for the words, the measurement is the evaluation results on the validation set. So for example, for a sentiment classification task, suppose they have a few training samples and the validation set, then they can utilizing the training samples to select the most probable words and fine tune on that and evaluate on the validation set to quantify whether this like the prompt is good for the sentiment classification task. Did I answer your question?
Yes. But that still cause some, in order to do that selection, we still need to do fine tuning, right?
Yeah, but I think they will claim that this template can be generalized for different kind of the data sets. All of them are for sentiment classification. For example, by like tuning on one sentiment classification data set, then a template can be utilizing on the other data set for sentiment classification. Even the semantic is a little bit different.
Then, okay. Then the next question is like for the template, it has to, so again, it has to have like some certain search space. Otherwise, it's like indefinite.
In here, they didn't search it. They just utilizing a fixed generating model to generate it. So for example, they give out this X and Y in the middle. They just tries to utilizing the T5 model to predict what should be the missing words in here, X and Y.
Then how about this great and terrible? Is that specified by human?
The great and terrible is already defined in the previous part. So they first say down the label word searching, and after that they will do the template searching, given a fixed template like the label word.
Okay, but we need to add some prefix and suffix to those great and terrible.
Yeah, this prefix and suffix X and Y is in exactly the tokens that we wish the T5 to generate them in like fill in blank words. For example, finally, what they generate is A and 1 with this X and Y.
Then what's the intuition here? So we can just, for example, as human, right, we'll probably just put it was great. And I don't know like what would be their choice. So
Yeah.
why the automatic generate one is better? I know like the number wise, they show it's better, but idea wise.
Yeah, intuitively, the reason is that suppose, so firstly, this great and terrible is appended because of the data set. We know that these sentences are a positive sentence, so we put a great here. So intuitively, the things they want to do is to find out the most probable, like the fill in blank words that can be used to generate this great or to be used to generate this terrible.
So it want to make them more natural. So then the algorithm will not pick up some shortcut, which is indicated by those X and Y. Is that the main intuition here?
I think no. I think in here, all they want to do is just to select the most probable one, and I don't think they they are trying to deal with the shortcut.
What I'm saying, like if we're not providing the most probable one here, as humorous, it's kind of we inject some artificial words. So probably the algorithm will pick up those artificial words instead of the most important great and a terrible signal. So that's why they want to make this X and Y very natural, meaning providing the most possible words based on the whole model, the generative model.
I think it is not like that, because that firstly, if the data set is balanced, for example, 50% is great and 50% is terrible, then whatever words we add, I think because the words we add is the same for these two classes of sentences, there should be a shortcut between them. And the second thing is that the goal of this X and Y is to lead the model to predict the whether a sentence is great or terrible. For example, in the test stage, what they will provide is just this X and Y, and this terrible is a mask token. So they will just based on the sentence and X and Y, like the template, to predict whether the missing words is great or terrible. So that the X and Y, the prefix and the prefix and premise, the goal is just to lead the model to predict whether it is great or terrible. This is why they're utilizing the T5 to find out the most probable words that should be appeared before terrible or after.
I see. So it's like the model will pick up the most likely word before great and terrible based on the observed text.
Yeah.
Okay.
Yeah. So for example, in this example, what they pick up is no reason to watch, a terrible one. It seems reasonable, and maybe I can show some of the other templates. Where is it? Yeah, for example, here. Yeah, for example, for this kind of the sentiment classification task, what they will do is S1, and this movie is maybe it's because that most of the the entity in this dataset is the movie, and for some of the entailment tasks like SNLI, which is a very standard dataset for NLU to describe whether one sentence is entailed to the other, then it's S1 mask and no and the other. So in this way, for example, if they have if they want to predict it is entailment, then S1 or right no S2. I think I think in this way, it means that S2 is entailed by S1. Yeah, I think it is very.
Then that raises another question: do we have are those X and Y are independent of the context, or actually at a different context, they're going to have different prediction?
So they were utilizing those. So firstly, when they get this X and Y, they enumerate all the contexts in the training data sets and pick up the best X and Y that have the highest probability over all of the data sets.
So that would be the same for this X and Y would be the same for all the places.
So it might not be the highest for each data point, but I think it is like a statistically highest over the whole data sets.
So that's the same X and same Y across different examples here.
Yeah. So after they find out the best X and Y, for example, here is A and 1, then they will fix it and utilize this in the whole data sets.
I see. Okay.
Yeah, for this part, it's hard to be contextualized. And I think the main goal of this line of the research is to do the few shot or zero shot learnings, because after they fix the template, utilizing a given pre-trained language model, they can already get a very good prediction results on many different tasks. So this is like the final evaluation they show. Like compared with the fine tuning on the small training samples, given utilizing these prompt-based methods, they can get a very significant higher performance over the few shot fine tuning setup. And also they are better than all different tasks. And also they here is like the curve. with different training samples. So actually, as you can see for SST2, with very few samples, like 16 samples, they can already get very good results compared with the fine-tuning baselines. And here are like the templates and the label words they extract for different tasks. If you are interested, you can also check out their paper. Okay, and also another line of research, another similar line of research is to do the soft prompting. It is that instead of utilizing the language as a prompt words or a template, we can just add a simple embedding there and tune the embedding for different tasks. So for this line, I won't elaborate more. If you are interested, you can check out the Liu Xiao's paper and also the Brian's paper about that. This line of research can show like a better intuitive empirical results, but less like interpretable. And also they also finally show that if the training samples is large, and this kind of fine-tuning will be less than the traditional fine-tuning methods. All right, and also more recently, there's also some of the works that instead of just utilizing the prompting to do some simple tasks, they also wants to do some harder tasks like question answering and machine translation by giving the model instruction. It is more intuitively like our human can learn not only from the data, but also from some highly abstract knowledge. For example, if a teacher tells me that like some algorithmic rules, then we can utilize this to generalize to all different like the data or input, instead of we need to like conclude some rules from data only. So that there's two papers here, and I will just briefly introduce their high-level ideas. It tries to give out again a language model an instruction, and wish that given this instruction, they can automatically know how to deal with different tasks. So for example, suppose we have a task set, suppose we have a task set here from different domains, such as natural language inference, common sense reasoning, sentiment classification, translation, and so on. And for different tasks, maybe we should have a different description of this task. For example, for translation, we should have a description like, please translate the source sentence to the target. For natural language inference, it should be like, what should be the next sentence given the current sentence. For the question answering, it's like, please answer these questions, and so on. And given this kind of different like the task and different like data format, the idea of instruction learning tuning is that we can find out some best instruction that tries to describe this task, and tries to teaches the pre-trained language model to deal with some of the tasks, and wishes that when you transfer to a new task and with a new instruction, they can generalize well with if the instruction can clearly describe the property of this task. For example, given the common sense reasoning, the instruction here is a goal: get a cool sleep on the summer days. And how would you accomplish this goal? Is how would you accomplish this goal is, and here is a goal, is a template. Original data is just get a cool sleep on summer days and some of the classification output. But in here, it tries to utilizing this template. How would you accomplish this goal? And put this option in the context, and just wish the language model can directly generate the answer. For translation, it is like the instruction is translate this sentence to Spanish, and the wishes that the model can directly generate the answer. And this is a plot from another paper, but the basic idea is similar. They can just give out some of the instruction for this input, something like respond yes if the sentence contains an explicit answer to the question, or we can do something like, in a task we ask you to write answer to a question that involves event duration. So for different instruction, the wishes that the model, given the same input, can give out the different output that solve different tasks. And the interesting thing is that in the second paper, they only trained on this dark blue part of the tasks, and tries to generalize to the other tasks like summarization and structure to text and even the translation. And final result performs quite surprisingly high. And for example, compared with the GPT-3 zero-shot learning, utilizing the additional instruction can help the model to generalize better to some new tasks, even without any label data. Yeah, I think this is the brief summary of these two works. So to sum up, I think this line of research tries to wishes that a pre-trained language model can encode all different word knowledges in within, and if it wants to utilize this pre-trained language model to deal with different tasks, we don't need to prepare much more data. Instead, we can just try to prepare a good prompting words to try to extract the specific knowledge from this language model. And through the pre-training or the pre-fine-tuning phases, if we add this instruction or prompting inside, then the model can try to learn given different instruction or prompting how to deal with different tasks, so that for new tasks, it don't need any additional like label data. Yeah, I think that's two direction I want to present today. Do you have any questions so far? Hello?
Hi, yeah, so I think I have asked lots of questions, so I'm good. So any other one have questions?
Yeah, if there's no further questions, we have two options here. One is that after this slide, I also put some of the works about self-training utilizing the distillation. And because currently it's 3 p.m., we still have 20 minutes left. If you want to hear about that, I can also present about that. Another option is that we can stop right now. And if you have any question, you can like just try with me offline.
I think we don't have to utilize all the time. Okay, so if you think it's like coherent topic, then we should be good. Yeah, I think the good things like if we can have like a more discussion on the topics that you have introduced, that would be the best instead of like covering lots of topics.
Yeah. So the reason I cover this prompting paper topic is because I observed that this is something like the new trend on the NLP community, and many people are very appreciative with this idea because that utilizing the large corpus it already like cover many of the knowledge that we wish the model to learn from some label data sets. In this way, for many tasks, we don't actually need the label data, but just from the unlabeled data itself, it can learn the intermediate knowledge. This is like a totally different line of research with graph GNN or the knowledge graph, which we explicitly tries to model this knowledge in a discrete manner. Like this kind of research is more like we wish the model can already learn all of this knowledge and store them in the huge parameters in the models. And
okay, go ahead, please.
Yeah, I just say that if people are trying to follow this line of research, maybe the trend is like training a larger and larger model with more and more data. And after that, maybe there is a very uniform or fundamental model that already know many knowledges. For different tasks, we just need a specific instruction or prompting to deal with that.
Yeah, so I still like, I think it takes time for me to appreciate this line of work. I think in practice, of course, it works, but to me, right, so it's just a kind of how we leverage the training signal. So instead of like doing fine tuning by treating them as additional tasks, let's turn it into a signal that's more similar to natural language, so we don't have to change the model, right?
Yeah.
So for me, it's just a yeah, it's a way, engineering way to leverage the signals. Okay, it's like oh yeah, I still didn't quite get why it suddenly give us a better performance, or like scientifically, what would be the deep insights here?
Yeah, I think the major lesson we know we can learn from actually from the original GPT-3 paper is that the corpus we utilize to pre-train actually already covers many patterns or the information we want to deal with some tasks. For example, at least for sentiment classification, mostly within the huge corpus, we can observe that after one sentence expressing some sentiment, there should be some description words such as terrible or good after that, so that utilizing the generative model, we can already learn such pattern to predict whether a sentence is possible.
I see.
Yeah.
So like if we treat as additional task, then somehow we just treat that task as orthogonal to the existing task. But now we somehow, although it looks like we just leverage the signal in a different way, but then in this way, we are able to also leverage in the patterns that is similar or correlated with the current task.
Yeah, so I think the major thing, the most important thing is that the pre-trained corpus actually covers many different things. So actually, there's also many interesting works that tries to pre-train on some mathematical like papers or not papers, like some textbooks. And actually, after that, when they're utilizing the generative model to do some simple equations, actually it can like give a good result even for some much complex equations. It looks like if the model can like look at more diverse and very complex data, actually the generative models, if it can generate quite well, it actually not learns some shortcut, but actually learns what is the hidden rules behind each equations. So probably this knowledge is just hidden in the neural network parameters. All we need is just to like extract it from the parameters utilizing this prompt or some others. This is like very contradict to some traditional knowledge thinking in AI, but probably this is also a line.
Okay, yeah.
Okay, then I think that's all for my presentation. And after that, I also attached some of the slides for self-training and the knowledge distillation. If you're also interested in that topic, please feel free to like send me an email and we can discuss that.
Okay, sounds good. Thank you.
Thank you.